Hey guys, welcome to System Design Fight Club. Today we're going to be covering the distributed tracing problem. But before we begin, if you have any ideas for other problems I should cover in the future, please see the Google Forms link below in the description, and I'd be happy to hear any suggestions. We're going to be covering the distributed tracing problem. This problem is actually a fair amount easier than I expected, and there's actually a pretty fair amount of material out there on it. It's actually pretty similar to the metrics monitoring service that was covered in Alex Shu's second book. In fact, he even called out covering how to handle distributed tracing as out of scope within the section. Otherwise, there's just a couple of little modifications you could make, and it would be pretty close to what we're going to be doing today. It's also kind of similar to add click aggregator, which is also from Alex Shu's second book. It's a little bit less related, but it definitely does have overlap and it looks a little bit similar. There's also a lot of like white papers that were put out by companies on how they're approaching distributed tracing. Most of them reference the white paper that Google put out on how they approach distributed tracing. It's called Dapper is the name of their distributed tracing service. I got a link to it right here. It had, like I said, very heavy influence on the other systems. I think a couple of the guys that worked on the other systems actually even came from Google and did the work on making those systems over in the other companies. I think one of the first major derivatives to come out was Zipkin, which I think Twitter made. Uber made a service called, I think it's Jaeger. They got a video on InfoQ about it. There's a transcript on the InfoQ website. They have a website just about Jaeger. There's a blog post on their engineering blog. Uber has a really solid engineering blog. One engineer from Uber actually went on to write a whole book about it. It's one of the PACT books, P-A-C-K-T. And the guy that wrote it is actually the same one that I think did the InfoQ presentation. So I think Uber's pretty passionate about their distributed tracing setup. Netflix also made a blog post and had some information that they put out as well about their distributed tracing infrastructure. It's on their blog. They also have an InfoQ video on it. Here's some other links that I was looking through for getting a good idea of how to handle this. And of course, there's a couple other proprietary products in the cloud services out there for AWS and GCP. Okay, so requirements. We want to have this DAG of the calls called a trace. Each call is going to be captured as a span. Let's kind of draw what I'm talking about is that let's say you're going to have some service A, and you're going to have a client request enter at this point, or this is where your trace is going to originate. It's going to call a couple other services. Let's say we have service B, have service C, and we have service D. So it's going to call all of these services just like that. And those services might have calls of their own. So could have one service that's just calling just another plain old service. So we could have B calling E and F. Have F. Have C calling a database. So we could have a data store over here. Call it data store G, and then we could have another one that communicates with a different service just over a message broker. So we have service H over here, and then we have a message broker over here. Let's flesh out the arrows for this. Yeah, B to E, B to F, and then C just does a write directly to a data store. D is going to put the message onto a broker, and then H is going to pull it off of the broker. And so this whole thing would be a trace, the whole thing. A, the call in, and the call out is going to be a span. B gets a span. E and F have spans, but they don't have any children on them. C also gets a span. You can't really do a span on a data store. You can't unless you like go into the code for Cassandra or whatever, or DynamoDB and are able to change it, or you make some kind of wrapper around it. I don't think that's really necessary. But it's going to be hard to have G emit a span on its own, and we're going to have broker. So if you have Kafka, you also are going to have some issues with that. But the whole thing's going to be a trace, and then each service will have a span in the trace. I'd recommend going through those links if you need a better way to understand how it's being how distributed tracing works and the value add of it. So there will also be people that can view the traces. I didn't add that to the requirements. You can view the trace through a web interface. Maybe there's some other ones. We're just going to stick with the web interface for now. We're going to have a start and end timestamp for each span. You should be able to view the trace. The traces and the observability tooling should be non-obtrusive to the regular query handling of the service. So you have a request coming in and a response coming out from the service to a client, and the tracing should not be obtrusive to the regular request handling of the service. A few minutes of data staleness will be fine on the reads. It's fine if our tracing data is not immediately showing up in the web interface that our end users will be using. It will be engineers viewing the traces, of course. Downsampling is permitted. So it's, do we really want to have a trace of every single request? I saw that for Jagger, the system that Uber created, it actually has a default of 0.1% sampling. Downsampling is the term from machine learning or data science, where if you have too much data, sometimes your model takes too long to train, and so then they will downsample the data so that the model can actually get trained within a reasonable amount of time. But the documentation usually just refers to it as sampling within the context of distributed tracing. Okay, and we're just doing this for internal services. It's not going to be exposed as an external product like X-Ray or Google Cloud Trace, but we do want it to run at the scale of big tech companies like Google or Amazon. And then we're going to use these numbers for what kind of scale we want it to operate at. It's quantifying what we want for our big tech scale is 1,000 internal services, 100 machines per service on average. 100 is a little bit on the high end. So I said on average, your external facing services are going to be a little bit higher scaled. So the ones handling google.com for Google, for like the web crawler and or the search engine, are going to be a little bit bigger and have higher machine counts. But we're going to say 100 on average, which is, yeah, for a lot of internal services, it will be kind of on the high end, so average. And 100 queries per second on average for each machine is how much they'll handle. That looks about reasonable from my experience. Databases can, of course, go pretty high. We're going to say 100 per average for each machine. And we want to retain the traces, the data for the traces for 1 year. Out of scope, we'll have metrics will be out of scope. In-depth logging is going to be out of scope. A lot of the products did have a little bit of logging that they'd handle, but for the most part, we're not going to have like in-depth logging handling. But I can show a little bit of how that will work. We'll come back to these. I'll make sure I cover them by the end. I just want to make sure that I do cover them. And with that, I guess we can move on to the numbers. So like I said, we're going to support 1,000 services. We're going to support 100 machines per service on average, 100 queries per second on average for each machine. How many queries per second on average per service? I got these numbers kind of adapted from Alex Shu's metric service thing. Like I said, they have a lot of overlap. So it's a little bit adapted from that. This number is the one that kind of came, that I kind of made up on my own. So how many queries per second on average for a service? So we are going to be handling, so we have 1,000 services, and it's, so we have 100 machines on average to service, and we have 100 queries per second on average for each machine. That comes out to an average of 10,000 QPS. We also had, what was the 0.1%? Didn't copy that over, I guess. Oh, yeah. So we're going to be sampling at 0.1% of the queries, because if we stored all of them, it would become obtrusive to the rest of the, it'd be obtrusive to the request responses for the actual end users. So we're going to do that, and then we're going to sample. So we're saying that our services are handling 10,000 queries per second on average throughout the day. So we are only sampling 1 in 1,000 queries. We have 10,000 queries per second per service. So it's going to be 10 queries per second per service on average, getting traced and recorded. So you're getting at least 10 traces. You're getting 10 traces per second on average. So that should be a pretty fair amount. So if you have an outage and you know, if it's down for like a minute, you're going to get about 600 traces to look at. So I mean, that's a pretty fair amount, and there's going to be variations. That's just mainly the average, but that should give you a fair number of data points every minute. So I think that looks fairly reasonable. How many queries in a year? Some DBs have a limit to what kind of to their how much data they can handle actually. For graph DBs in particular, Neo4j has a limit of 1 billion records, I believe. Time series DBs can be sharded, and Cassandra, and of course most regular OLTP databases that you're going to use can be sharded just fine. But this will affect our choices a bit if it's a large enough number. Okay, so we are doing 1,000 services, 100 machines, 0.1% sampling rate. So we have 1,000 services, and we're doing 10 queries per second on average for each service. So times 10 QPS, it's going to come out to 10,000 spans getting recorded every single second. And then how much is that in a year? So we have 10K spans per second times 100K, just the number of spans in a day. So that would be 1,000 times 1,000 times 1,000. So that'd be 1 billion in a day, or hold on. Yeah, that's 1 billion in a day, and we would have 300 billion in a year. Services. Yeah. Okay. So that would mean that we can't use a graph database. So we do have a retention period of a whole year. if we reduced it down to a day, or we decreased our sampling rate to like 1 in 10,000 or something, maybe we'd be able to get away with a GraphDB a little bit more. But GraphDBs also can't be sharded, and we are saying that we're going to do 10,000 writes per second. And if you can't shard, that means you're going to have to do vertical scaling instead of horizontal scaling, which means getting a beefier server. And you generally don't want to do that, because you can only make your server so beefy. Your machine can only get so beefy and handle so many instructions at a time. And you can only fit so much data down your Ethernet cable. So that's going to kind of rule out using GraphDBs like Neo4j. How much data in a year? So we want to have, we're going to have 2 timestamps per span. So 2 timestamps. We're going to have a couple IDs per span. We're probably going to have a UUID in there, which is going to be one of those, it can be written as one of those weird chains of characters, like we've gone over that before for UUIDs, but that can be like 20 characters. We'd say between all these, it might come out to like maybe 100 characters. So these would be Unix epoch time. So we can do those as ints, which is 4 bytes each. So that would be 8 bytes there. And then, like I said, one of those is going to be 20. So you're going to have at least 20 chars for one of those. And then if the other ones are also ints, that'd be another 8 bytes, but like 100 bytes possibly. So 0.1 kilobytes with just that information. And then if we're going to do logging, let's say that we have maybe, if we're logging the request and response blobs for each span, let's say that's 1 kilobyte there. And then, so just with the request and response data, that's honestly kind of low. We're going to round that up when we're looking for the total amount of data for a request. Let's say for the logs themselves, we're going to have those attached to the span. So this, let's say this emits some logs while it's doing its own calls. You can associate those with the span. Let's say that it's 10 logs per request handling within a service. Let's say they are 100 characters each. That comes out to 1 kilobyte. Okay, so that's 2.1 kilobytes total for each span so far. And like I said, those numbers are kind of low. Let's maybe round it up to 5 kilobytes per span. So then we would have maybe 2 kilobytes in total for the request and response data, maybe 2 kilobytes for the logging, and then we even have another 0.9 kilobytes to spare. That request and response data can actually get pretty large sometimes. Okay, 5 kilobytes per span, and we're going to be recording 300 billion spans in a year. We're going to do 5 kilobytes times 300 billion. So that is going to be 1,500 kilobytes, 1,500 billion kilobytes. So 1.5 billion megabytes, 1.5 million gigabytes, 1.5 thousand terabytes, 1.5, I think it's petabytes next. That's a pretty fair amount of data. 2 petabytes is kind of a lot. Not for Google scale, but I mean in terms of like a single hard disk, I don't think you can get a hard disk quite that big. I don't think that's, at least commodity ones, I don't think are going to be common at 2 petabytes. You can maybe do two terabytes for a hard disk is easy even for consumers. You can get that on a laptop even. 100 is probably even reasonable. So that would be like maybe 15 hard disks. you might do some like replication or something as well of the data. So it's maybe going to come out to more than that, but it's like 15 hard disk is not anything crazy. So we might be storage bound, maybe not, we'll see. We can go ahead and hop into the diagram and looking at how the system is going to be looking. So the spans are going to be kind of created as logs, and then we want to collect them. So we're going to have a span collector service. And do we want it to be a push or a pull? That would impact whether the retries would be on these guys or whether it'd be on the service to figure out. I kind of like it being on them to figure out what the issue is, rather than this guy being responsible for hitting up all the internal services and whenever it's starting to get fatals and being like, hey, please configure it correctly and redeploy your service. You don't want to have, if I haven't already clarified, you don't want to have the traces being emitted immediately with each request, because then on top of the 100 requests per second that a machine is handling, or 10,000 per second for a service, it would be also 10,000 going out directly to the collector service, and then this guy would be getting that times the number of services. So then this guy would have to be able to absorb 10 million hits per second. So it'd be better if we just kind of group up those spans within the machine, and then we just have like an agent or something that is passing them over asynchronously. So we're going to draw a little agent box and say, nope, agent. We're going to have that. So we have a little collection agent on all of the machines. The services are of course horizontally scaled out. So each of the machines in the service is going to have the little agent on it. And every so often, I said I want it to be a push. So that means that this is going to make the request over to here. So we're going to have the requests going out just like that. You can't deploy an agent to, it would be trickier, I think, to get it running on Kafka or DynamoDB or Cassandra or something like that. I think, I mean, I know that, well, so sometimes the thing is provided as a software as a service instead of just like, getting a bunch of EC2 instances. And then you're like, okay, I'm going to run PostgreSQL on these EC2 instances. So for example, with DynamoDB, you do not have direct access to machines, so you can't get the agent on there. If you're just running, I think AWS does offer hosted Kafka. You're not going to be able to stick the agent on some of the machines though, like I said. So this is not going to have an agent. This is not going to have an agent. Yeah. So the agent is going to send the data over to there. What's the data going to look like? And then what are we going to do downstream? We're going to have this thing receiving these batched up groups of it. So the agent will also generate the UUID. Where does the sampling where's the sampling performed? I think I had that recorded in the things that I want to make sure that I call out. Yeah, downsampling should be occurring at the root, the source of the trace, the thing that originates the whole trace. Should be the one that figures whether or not it makes the tracing decision and propagates it down. Okay, let's kind of talk about how that's going to look. So we have maybe a call between A and D, and the request is going to look like this. It'll have all of your regular data, in there, your just normal attributes that you're doing for communication between the services, but you're going to want to have some extra stuff in there. You're going to have a trace ID, which they are all going to have in their communication. I will also make this data also needs to be in the messages on the broker. You're not going to be sticking into your own databases though. So this would not have the trace ID in it, but everything else basically is going to have that. So you want a trace ID. You're going to want a span ID, and then so you don't want to pass the entire thing of metadata down the services with it, because if you have something that's 5 or 6 service calls deep, particularly if you have message brokers, you can definitely get that deep because it's being made asynchronous. That could be a lot of data getting passed down. So you want to keep it minimal, and then the collector service or your distributed tracer is going to rebuild the whole trace for you. So you want a trace ID, you want a span ID, you might have a parent span ID. So you're going to have the trace ID, which will be for, if you have one request come in, all these nodes are going to have all the machines that pick up the request are going to have the same trace ID. And then the span ID is specific to the machine. And then you're going to pass down your span. Oh, so you only need to pass the span ID. You don't need the parent span ID. You want the parent span ID to get collected in the log though. And so then you would have, this guy is going to be the originator of our trace ID. So we're going to have a trace ID that'll look like EF, ABC, 1, 2, 3, EF, ABC. It's kind of UUID, so that you don't have to, you can generate those without having to call a centralized service. I think Twitter had a really nice blog post on how to generate UUIDs. There's a whole chapter in one of Alex Shu's books about it. We're not going to deep dive how to get those. It can be a part of the agent itself generating that UUID. And the span ID, we're going to say that this is the A span. I guess we could just go ahead and have it would just be it would just be the service identifier as the span ID. So we would say that is the A service. In that request from A to D. And then when we're talking about service, let's maybe talk about, so this one has a message broker, and that's why it's like a little bit more complicated. Maybe what we should talk about A to B instead. It still look just like that. And then when we're talking about B to F, we would replace A with B. And then what are the logs that we're going to send over there going to look like? So it would look similar, but we would also want to have the span ID. And so then when we're talking about the one that D is going to emit, its own span ID is of course going to be D, but we would have the parent span ID, which is going to be A. So it's going to receive the parent span ID in the request that comes in, and it'll mark that as the parent span ID in the logs, and it's going to mark its own span ID identifying itself, and that's going to get passed up there. We are also, this is the log data. I'm not talking about the request between D and the message broker. I'm talking about what is going over to the span collector service. And we also want timestamps. I also mentioned that. Traces are also good for determining where latency bottlenecks might be in your service. That's a whole thing at if you have an external service, you might have SLAs for what your service should have. And so this guy is going to have SLA of, you generally want your page load times to stay under 2 seconds. So wow, the arrows just got totally screwed up from that. I can't fix that. You generally want to keep your pages loading in under 2 seconds. So this guy is probably going to want only 2 seconds to pass between this request in and this response out. And so that means that these guys' spans need to be, the sum between all their spans has to be less than 2 seconds. And so then that turns into a whole political thing if service A is not owned by a team in the same org as service D. Yeah, that's a whole thing that I remember from my time at my last company. Okay, anyways, timestamp. You want the start timestamp and you want the end timestamp. And we're just going to do Unix epoch time, which of course has some issues. There's alternatives where you do the thing where it's like 2022, 1020. That's like the date, and then you do T, and like that. We're going to stick with Unix epoch time because that would work fine in our case right now. And it would look a little bit like that. And then the end time would look a little bit like that. We'll say it's 1 second between the start and the end. So are we doing the timestamp? Are we recording our own request and response? And are we also recording the spans for all of our child calls? So what if D has an outage? That would mean that it can't record its own spans. That means that A has to record the span for its request and response from D. So you'd have to do that. And then let's say it is online. We have the request and response for when it goes out and into A. And then there will be some network latency. And then you'd have D doing its own stuff, and the time between receiving it and the time between sending it back out over the network. So for the sake of debugging latency issues and deep diving where your latency bottleneck is, you might want to just go ahead and record the span on both the parent and the child. And then I have parent span for reconstructing the logs. Another approach was where you could do another approach was, instead of having the parent span ID, you could instead record your children. So instead of having your parent span ID, you just have your own, and then you have children, and you would go like, you have a list of all the spans for your children. So for each one, you would do, you would have their own span ID, to have their own start time and end time. You can maybe even record the status code if you want to record the entire request and response for each of the children as well. I think that would make this a pretty big blob object. So the alternative approach is that instead you have, so this is one approach where you store children within the blob. The other one was you have the parent span ID, and then you would also have children on. Hey, sorry about that. There's a little hiccup on my end. So like I was saying, you can either store the children on the, so you have the incoming span kind of getting recorded, and you can store the children calls over here on that span, and that's what that would kind of look like over here. And you'd of course have multiple children. So this one has BCD, if that was what we were modeling. And then the alternative approach is that you have your so if we were doing the incoming span for A to D, and you start the span for the request that you have received, you have that. And then you could also have the child spans. So you have the span ID you had it's D, your parent is A, and then you also have okay, let's maybe switch to B because it's a little bit more straightforward than the message broker. So we have A to B, and so we have the span at the top for B receiving A, that's this one. And then we say that we have the call that B is making to E. And so then the parent span is B and it's calling E. And so then we would also have that, but they're both going to have that same trace ID because it's getting passed all the way down through the stack to all the calls that we're going to have to make. So the thing that H is receiving, this span right here is also going to have that same trace ID. It's going to be on all the machines in the trace. Okay, so we have that part there. And so this is a bit, it keeps each individual span object smaller, which I kind of like, because you might also be storing stuff in there, like you could have the entire request and response blob and the logs. So you would have, we're going to stick with B again because it doesn't have a message broker or database right. And so again, we're going to say that it could have the request blob, it could have the response blob, it could also have a list of logs. So like I said, you could have maybe 10 logs at 100 characters each. We left space for having maybe 20 logs of 200 characters each instead, which is way more realistic. We're not going to get really in depth with logs handling though. But you can attach some logs as well. And that's where that would go on the thing. And you wouldn't have any logs in these spans though. You're just going to kind of keep them as the ones on the client, on the client, they're just like the client stubs. And then over here, well, I guess you could probably record the request and response blob as well for each of the children, because then if the downstream service has a 404, well, sorry, that's a message broker between them, so you can't do that. But if C is out and you're making the call from A, you could still have the request blob for A, and that's you could still have the request blob that you were sending out from the service over here. You wouldn't have any logs though, because of course you don't have insight into the logs from the child services. And you don't want to pass those back up. That would add extra latency, and you want to be unobtrusive to the normal request and response stuff. You just want to write out some logs to some files and asynchronously collect them over to this thing. But that is how you could make those logs work. How that'll work between you could have a parent or child flag to distinguish between the EB span on this services side versus the one on this services side, because this one's going to have the one with just the request and response blob that it wrote out, while this one would have maybe the logs as well. And so you can maybe have as parent flag or something like that. Sure, let's go ahead and write it. Or we'll call it is child flag. And then it would be true for this one, and then we want it to be false over here. So we're going to do that. So true, it is the child of that parent span ID, while, so we're talking about B's logs over here. Okay, so in this case, it is the child span that it's recording. Well, in this case, it is actually the parent span. Yeah, and these are logs getting sent from B over to there. I have them over by the arrow from A. I understand that's a little confusing, but yeah, I'm talking about B. Okay, I think we've gone over that a lot, and I want it to be a push, so that way it's the service owners over here that would get paged if they haven't configured it correctly instead of the span collector service. And then the span collector service, we're going to want to have a data store. So it would be the trace data store. Let's have it centered. That should be like that. Nope, I did not ask to open the dictionary. So we have the trace data store. The span collector service is going to be receiving those, and it'll want to write them to the trace data store. So I think we've already gone over that. It's maybe not a good idea to use a graph database because Neo4j is the most well-known one. I don't really know of other ones really well, although I recall that there's definitely a couple of white papers out there. I don't know if they made those externally available though. Neo4j is the only one that I know of that's like more available for everyone to use. It's anyways, Neo4j can't be partitioned, and it has a 1 billion limit, so you can't use Neo4j or a graph database for this data store. So what are some of the options that we can use? So Cassandra's one, it's going to be write heavy. We are going to have a browser for the engineers. It's at some point we're going to be having a browser engineer analyzing trace data. So at some point it's going to be talking to a browser, and there will be a backend for retrieving the data. Trace service backend viewing is for viewing the traces. So at some point we're going to have some kind of backend, and it will be fetching the data out of the data store, and then it'll be putting it into the browser. And this will be a much lower volume than the amount that's going into it. Although I guess this would be at it'd be aggregated, but still it's going to be write heavy. It's definitely going to be very write heavy over here, and so Cassandra makes a lot of sense. I guess Dynamo, well, I think Cassandra makes the most sense. We already ruled out graph databases. You could maybe use a time series database because we do have time data. So that is another option because we have start timestamp and end timestamp. But are we primarily going to be looking at it over, or is that really going to be the main thing that we're going to want to sort it over? What is the schema going to look like? That will help us make a more informed decision as well. Let's think over how the schema is going to look. So we are going to want to have the trace ID, have the span. So this is going to be part of it. I'm sure there's a way to do this without the isChild flag. I'm just leaving it in for the sake of being pedantic and correct. It's going to look a little bit like that. You could have a request blob and response blob object. You could have the logs in each record. We're going to want to have all of that data for each record. And then I think that's all we need. That's all I can think of right now. I like this object a lot more than if we were trying to store the children on it. It's more fun to store the parent span ID. A graph database made sense because it's a DAG of objects, and if you're trying to reconstruct the span if this thing's trying to reconstruct the span, the primary value add of a graph DB is not, it's not more performant necessarily for graph data. it has a different syntax other than SQL that makes it more convenient to do the recursive calls for a graph traversal. But it's also going to be a little bit more latent. I've heard they're usually a little bit more latent. And then of course we already ruled out graph databases because it's Neo4j can only store up to 1 billion nodes. Unless we try to figure other parameters, but it's you know, we want this to be scalable, and if we're going to force ourselves into vertical scaling, we're just not going to have a good time. So we're not going to do a graph database again. But it would have been way more convenient for trying to reconstruct the traces. Of course, that's why it was being considered. Okay. Oh, I forgot to leave the timestamps in there for the traces. That's also really important. Do I have that here? Okay. How are we going to index this? So timestamps are both great candidates for indexes. They should not be primary indexes. You do not need that for primary index. This is particularly important. I think that can be the partitioning key. So these are services, and these are identified by the services. I have the service names on there. So the identifiers can, of course, have a celebrity issue there. We have, you know, the main external services that are possibly just generating a whole lot. And then maybe you have some other auxiliary services that are just not really receiving a whole lot of requests, and they just kind of help through doing aggregational queries or something. So you might have like C, and then you have something else reading off the database. And so then that would be where you would have much lower volume. You'd have a lot less requests as if it's a more internal facing thing that needs traces as well. So you can have a celebrity issue going on with the spans due to the varying traffic between the services. So you don't want that as a partitioning key, because that can result in a hot partitioning issue. So partitioning key would be preferable here. These are also going to be candidates for secondary indexes though. So maybe a sort key. That one is going to be so partitioning key, sort key, that will also be part of the sort key. And then we had, due to me being pedantic, there's the parent span, then there's the child span. And so this is actually also going to need to be part of the primary key. So that's also going to be part of the sort key as well. Yeah. Okay, and we already said that our data can be stale. Eventual consistency is going to be good enough on this database. I'm leaning towards Cassandra, and that is actually what was supported by default in Zipkin. Zipkin originally supported like just Cassandra, I believe I've read. So I'm liking Cassandra a lot. And then, well, so the last piece of the equation that you need for determining Cassandra or time series DB is like, how are the engineers going to be querying it? Is it going to be a key range query, or are they going to always have the trace ID and know what one they're going to look up? Well, so when are you going to be looking at it? It's when maybe you're trying to inspect a latency issue, or you're trying to look at, hey, why is our service down, or why are these certain queries acting funky? So you could maybe pull the trace ID out of the logs. You could look at the logs for any of the requests that you've been handling, but you can only look at traces for the ones that are sampled. You would only have the sampled ones to look at. Something that might be useful to pull out of the response blob from the downstream one that you would have on the parent. No, you'd have it on the child ones, on the stubs. You would maybe want to have the status code pulled out as well, just for convenience. So you would want to be looking at, like, for example, for the 500 responses coming out of your queries, you want to look at like where, so a lot of them are probably going to be 200 responses in the status code. So let's throw in a status code field. It'll be like 200, 404 potentially. And that would be if it's a child. So let's maybe put it over to true just for the sake of explaining this. So 200, 400 or 500 for internal server errors. And then you would maybe want to also add it as a secondary index. So that way you can just go ahead and filter it out a little bit more easily. Although I think if you're filtering it down by these already, you maybe don't need to add the status code. Every time you add another index, it speeds up your reads, but it means that your writes are going to be a little bit slower. And we are definitely going to be write heavy on this service. So I'm going to say maybe secondary index. Depending on how those queries are going to look. So what are you going to be looking for? So you might already have a trace ID in your logs that you pull out and you're looking at it, or you're trying to find, let's say that a query comes in and the engineer is thinking between 1, 3, I'm going to talk in Unix at block time. Between these two times, show me traces for requests that were they had errors in them, or that had oh, you could maybe have the delta. You'd maybe want to pre-compute the delta, and so you would maybe just want to look at the highly latent response times that were, so you just want ones that were 500 errors or something like that. You could maybe even be a bit more specific to that. So you would have maybe specific messages when you're doing those 500 errors on top of using like specifically 501 or 502 or whatever. Or when you give like a 400 bad request, for example, you would definitely want to tell them why it's a bad request. You don't want to just give them a 400 and be like, you didn't format your JSON properly. You want to tell them like what attribute was missing or why that attribute was wrong. So you would usually have also a message. So maybe you could filter down by that. That would maybe also be a nice convenient thing that you would want to extract. Maybe like a status code message field, also extract out for convenience. And I said you might want to pre-compute the timestamp delta if you're looking for. So another thing that they might be, another example would be show me traces for requests that took longer than 3,000 milliseconds, so 3 seconds. So you usually, that's like a rule of thumb from, I think the book called Don't Make Me Think, is that you want web pages that load in under 2 or 3 seconds or so. So if it takes longer than that, you're more likely to have users that are just going to click out of the page or kill it instead of waiting the full 2 to 3 seconds. Particularly if it takes longer than 5 seconds. Not a lot of people stick around that long. It's like if you're on Amazon.com and you're trying to look for a certain product and your search key is 5 seconds every single time you change your query a little bit, they're going to get annoyed and they're going to go look somewhere else. Show me things that took longer than that within a certain pair of time, and maybe it could be like over the course of the entire day. So maybe it would be even we could say 138 5,000. I don't know if that comes out to a full day. It's 100,000 seconds. 1, 2, 3, 4, 5. So that'd be over a couple of days. Maybe there's not a lot of latent requests, and so you would need to increase this time span a lot, or you're just looking at the tail end errors. So you could have a bigger range that you're looking over. So if you're seeing a lot of requests that are for larger, so a lot of these are going to have a 200 status code. I'm thinking that we probably want to have a secondary index here. I'm thinking that we probably want to have that secondary index, and then it might even make sense to have that. You might be looking for a specific status code message, such as missing, what is it? Wumbo attribute. So maybe service E expects to see this attribute called Wumbo or something that they just added, and they forgot to tell all their clients beforehand that, hey, you need to add this Wumbo attribute that we're rolling out. So might make sense to index that, but you generally don't want to have a lot of 400 and 500 errors. So I don't think, I think we're fine without that. Then also if we did try to index I guess we could use integer identifiers, but then it'd also have to be unique across all the services. That's not going to happen. And you would need to do like an inverted index here. I've honestly not read a lot into how inverted indexes work. It might be expensive. Also, what databases actually support it? I don't think Cassandra does. We would need Elasticsearch there. Oh, I guess that's another thing that we can maybe have. Maybe Elasticsearch would be nice. But another thing I was getting at is that you would probably want to have a message broker between these two things for improving the availability, particularly if you're doing Elasticsearch. I don't think that one's designed for high availability. Cassandra is, but if we're going to be using a couple more indexes, that'll increase latency. And then that's how decreased availability manifests, is if your writes become too late, and then you might have a little bit of degradation in your availability. Anyways, you're going to do that. You can't actually have a broker talk directly to your data store. I think a lot of people omit this, but you do actually need to have task runners pulling off the messages and then writing them to the data stores, how that works. So you pull it off the message broker, and then you can write it to the data store. You can't just go straight from broker, so I'd be using Kafka. So broker, Kafka. And then for task runners, you can go ahead and just use, or Kinesis, if you're on AWS, Kinesis works just fine. And it also does partitioning or sharding for the stream, just like Kafka does. And then you can have just a Lambda function set up as a Lambda trigger off of each shard. And so you just have, I'm just going to say task runners, Lambda fns. Oh God, that is atrocious. Jesus. There we go. That'll do. Okay. Okay. Does it make sense? I think the main value add of a time series DB is that it also, just like a graph DB, is just more convenient with syntax than having plain old SQL. Cassandra makes the most sense. We're right heavy here. We want Cassandra. Elasticsearch isn't necessary. Cassandra supports a fair enough number of indexes on its own. DynamoDB has a limit of like 25. That's why I was thinking about it a little bit more. Elasticsearch is a search engine. It can support a very high number of indexes. Well, so if you wanted to start finding specific things in the logs in the traces, specifically traces that had a certain log message. So I'm a little bit split between Cassandra or Elasticsearch, but I don't know if a time series DB really makes sense. That is my discussion here. Let's go ahead and stick with Cassandra because we know it's going to be write heavy. Time series mainly for the convenience of the syntax. It's a more convenient syntax. Cassandra will work just fine. Elasticsearch is a nice runner-up though. So Cassandra's my final option. That's mainly because I know that it was the default that Zipkin used. Yeah. Okay, so we got that figured out. The trace viewing service would make a call to this. It's a query. It's going to be lower. It's going to be way lower volume than these. Like I said, the writes. I think I already talked about the write volume. We had it coming out to 300 billion in a year. And it was 10,000. Oh, it was 10,000 QPS on average writes. Okay. So 10K QPS for writes. I don't think the engineer is going to be checking out the traces at 10,000 QPS. We definitely have these key ranges here. I'm pretty happy with my choices right now. I'm pretty happy with my choices. What else do I want to go into? Let's go through the call outs. Oh, it was okay. Maybe some estimates, maybe some machine count estimates would be nice. Let's check the call outs and then we can go into machine count estimates. Okay, data store choice. I'm happy there. It's really interesting aspect. Alex Shu's metric service chapter also had a nice discussion of data store choice. It was very similar. It was also very write heavy. I think he went for a time series DB for the metric service. I like Cassandra. We'll stick with that. It's very standard component. Can a popular downstream internal service get flooded with even when we're doing downstream? Okay, so we've got this, and then let's expand it a little bit and say that we've got, let's say we've got our little service E over here, and let's say that E is a popular boyo. He is just receiving a, he doesn't have any dependencies below him, which is a sign that he might be what Amazon calls a tier 1 service, where you're supposed to minimize your dependencies as much as possible. And then you might have a whole bunch of guys that are calling you, a whole bunch of other services. And so it's not external facing, it is an internal service, but it is just being used by a lot of different things. So an example would be like the A/B testing service for rolling out new features in all of your external services. So we've got, let's say that we've got google.com over here and we've got YouTube over here if you're a Googler. And they both use the same internal tool. It's a shared tool across the whole company. You can even say maybe even Android is using it. So we've got YouTube over here, and we've got Android, and they sometimes need a phone home to feed all their spyware data to when they're phoning home or whatever. So they're doing internal service calls too, and when there's a new feature rolling out on Android, it requires some coordination with the server on updating the whole phone or whatever, and it's also using the same A/B testing framework. And this is just a popular boy. He actually receives even more traffic than google.com because just everyone is calling him. So could this result in this guy still having a lot of traces that need to be sampled? Yes, it would result in more, but so this guy is sampling at 0.1%. So 1 in 1,000 requests that he makes are going to have traces that go all the way through. I should actually talk about why sampling precision is made at the root. That's a really good thing to talk about. So 1 in 1,000 of the traces are going to result in this guy having a trace that will get written over to the collector. YouTube is also making requests, and 1 in 1,000 of those are also going to have spans that are going to need to get written. But so you have 1,000 requests coming in over here, 1,000 over here, and for each of those 1,000 requests, you get 1 span generated. So he's going to be making more spans, yes. But overall, it's going to make a lot of requests. Yes, there's more spans getting created, but I would not say that it's a flood because it's proportional. It's proportional. It's a popular service. So I actually even covered that, is that we could get a hot partitioning issue off of the span IDs if it was the partitioning key, because some services are more popular than others. And I actually had specifically said in that example in the DB schema. That's hilarious that it's so conveniently we had E being used. And if that was the partition key, we would have gotten a celebrity issue off of that guy having so many more traces. But thankfully we knew that already. So yes, he's going to have more. It's going to have more spans, but it's flooded. I mean, yes, it's going to be more, but it's not. It should be designed for that. We shouldn't have. We can't actually be getting sampled at a lower rate than its parents, because then you would get incomplete traces when you're reconstructing them over here. I should maybe talk a little bit more about how that query looks as first. So you're going to find all the root. You're going to look at a time range, and you're going to have a service that you're going to be looking at. So you're going to filter down. Filter by, so this is where your indexes are going to be coming in handy. So by service name under span ID. So you're using the span ID as part of your where clause in the SQL. And then you're going to have maybe status code, or most likely timestamps as well. And again, timestamps would make a terrible partitioning key because a lot of the query is going to be for the most recent data. So you're going to have that. You'll get back some some trace IDs for your service. So you'll have, let's say that this is a two-step thing. You see a list of traces, and then you click on an interesting one, and then there's a detail page. And so then there's a second step. So this is the first step. So first step, list off some traces for your service and pick an interesting one. Return the full trace. And so this one's just looking at spans, while the other one is retrieving a full trace. Turn the full trace of the given of the selected trace ID. And then that is actually still going to be a key range query. So this first one's definitely a key range query, and you're using those indexes to filter it down. This one is still a key range query because trace ID is not uniquely identifying. You need the, so our full primary key is going to be, you need all four of the first attributes for the primary key. So you have the trace ID, and you'll leave it at that, but you would retrieve the full tree of so over here in our example with A's trace IDs, you'd have 1, 2, 3, 4, 5, 6, 7, 8. I should talk about how that works. Yeah, that'll be a fun discussion. So you'd have 8 different calls returned from our example. So return the full trace of the selected trace ID. I don't think you need any, you don't need anything else beyond that. So filter by just the trace ID, and then you'll get back 7 to 8 spans. And so this was, well, oh, okay. So I guess the graph DB doesn't even really help all that much since you're filtering down by the trace ID, which is going to be in all of those spans. So you don't need to make recursive calls. You don't need that's what the GraphDB's main advantage is that when you're doing a graph traversal. Well, in this case, I guess we're not doing multiple recursive calls, we're just doing a single key range query, and so the GraphDB doesn't even really add as much value. Even though we have a DAG, you're just going to have the DAG just going to get reconstructed off of it's just a handful of data points, and so you can just do the reconstruction on the backend itself of those 7-8 data points. So that's fascinating. I did not actually expect that. Very interesting. Okay. Pull or push for the collector service. I already talked about that. I think it should be a push because then it's on those client services to figure out the configuration issue, and then they can do the exponential back off instead of you calling them. And then like if it's misconfigured, you're gonna be like, huh, I'm getting back these 400 or 500 errors, or it's probably a 400 issue or a 404 if it's a permission issue possibly. So it would be a config issue. And then it'd be like, what do? I have to then forward the page to them to redeploy the service with an updated agent. And so it doesn't really make sense for you to get the page for them being down just to forward it over to them and tell them to redeploy their service. So they should have it, and then the agent should be properly configured for exponential back off or whatever. Yeah, so I think it should definitely be a push. Why sampling decision is at the root? Well, so you need to reconstruct the full trace, and so the decision has to be made here and propagated down. And so if you have one that's not in the sampling group, you'll just not include the trace ID and span ID, and it wouldn't be propagated as well. So it's like you can use the absence of the trace ID to indicate that we're not going to be logging the tracing for this one. And you need it to be consistent for the full like tree of requests, because if you did the tracing decision, the sampling decision independently on these child service calls, then you would not be able to rebuild a full trace. And you want to always be able to rebuild the full trace for the queries you're interested in. So that's why you have to do that. It has to be at the root, the originating. It has to originate the trace. How does the DB and message broker traces work? So a message broker is an asynchronous call. So this is a synchronous call. This is an asynchronous call, and so you can just attach that trace information as part of the message. And it's a message broker's asynchronous call. And so you would just have your message, and so then you could include message info, and then you just go ahead and include the trace ID if you have it there with the with your span ID. You want to pass down the parent span ID, of course, to the child, because this guy could even have multiple different people writing to the broker here. Could have multiple different parents to talk to. So you might want to identify which parent sent the message. And then you have the rest of the info, and you don't need to include the timestamp info from the parent. That can show you how long it takes to get the message over the broker. So that would actually be helpful, because then if there was a downstream outage of H, you can even tell how long the outage was for by looking at the delay between your end timestamp on D and the start timestamp on H, and then you would see how long it was in this broker for. And then it can continue further downstream like normal to any other child requests of H. Okay. Oh, and then for DBs, you can have a span for it on C. This one would have a stub. and then you can just have a hard-coded span ID from C. You would say the child is G in your stub, your thing where his child flag is set to true or false, the stub between C and G. So you would write G, so you don't need to worry about G identifying itself because you're identifying G in the stub. Yeah. Machine count estimates. That's what I'm missing. Okay, machine count estimates. How many do we want for the data store? Is it actually going to be storage bound? Could it be bandwidth bound, or what is the bandwidth that we're sending down there? So we already identified that we're probably going to need like at least 15 hard disks. And I mean, you can have like network attached storage, but I don't know. How much data are you sending over the wire? Well, it's also 10,000 requests per second, and some databases can go that high. Can a machine handle that number of requests? Oh, okay, they're also going to be compacted into these things. So depending on the compaction rate, the amount that how often you send the logs over with this push. I mean, it would just be it'd be a fewer number of requests getting sent over to the span collector service, but they'd be much bigger requests that you stick on it. And then you can have up to a 1 megabyte message on broker. Oh, well, so then if we have 5 kilobytes per span, and on average, so if we have 5 kilobytes per span, we have a 1 megabyte message, and then we would just have this one maybe doing the splitting for us to make sure it's the right sizes. So 1 megabyte is 1,000 kilobytes. Divide that by 5, that would be 200 of 5 kilobytes. So you could maybe put 200 messages together. We don't actually want to, well, I mean, I guess this thing can actually optimize it to pack the messages into Kafka as optimally as possible, or you can do something in the agent for optimally packing that. But we can probably bring down the number of requests per second by 200. So we were doing 10,000 spans per second. We can bring that down by 200. And so we have 1,000 divided by 20, which is 500 divided by 10, or 50 queries per second instead of 10,000. Okay, well, that's even, I've definitely seen machines able to handle 50 queries per second. They're going to be large messages, which is an interesting thing. Well, so it's 50 large messages of 1 megabyte each. Use Snappy or whatever and compress it over the wire. That's actually a common thing, is to actually compress your stuff before you send it over. In fact, if you look at your browser's network inspector thing, you'll see that most of the packets are, I think they're compressed with gzip. So I mean, you can even get this smaller. Maybe you can, I don't know if you would want to compress it over Kafka. Well, you can compress part of the message over Kafka. Let's focus again on doing this guy's count. So 50 of 1 megabytes, that'd be 50 megabytes per second, or 0.05 gigabytes per second. in there. So you can definitely get an Ethernet connection of 1 gigabit. I don't know if you can actually get 1 full gigabyte. I've actually looked into what kind of internet connection you can get on EC2 instances. They like to do the stuff where it's like up to 10 gigabits, but they say up to, and it's because it's burstable, and so that means they charge you extra for it. So it's actually 0.05 gigabytes, which is 0.40 gigabits. Not even 1 full gigabit. So you're not going to be network bound. So not network bound, 50 queries per second. I guess you can handle that with 1 machine. I guess 1 machine. Well, so you would maybe you usually want to do like n+1. So you would have 2 machines handling 50 queries per second of 1 megabyte. You want to do n+1, so that's why it's 2. You can do a rolling update. You don't do, I mean, I guess you can get away with 1 if you do a green blue flip whenever you do a release or update of this thing. I like 2 though. Okay, and then that's only 50 messages that you're writing of 1 megabyte, and so that's not crazy. Okay. I think this thing's really going to come out to be storage bound. Yeah. So this thing's going to be storage bound. Heck, you might even want to not do Cassandra. It might even make sense to do something like Dremel or BigQuery. Might even make sense if it's really going to be all that storage bound, where you can have like 1,000 hard disks per machine. But we're not that storage bound. But you can look into something that's a little bit more optimized for that use case. Maybe Presto and Trino are optimized for that a little bit differently than Dremel. Hive actually was a thing that was written at Facebook as a modification of MapReduce to make it work better for their use case, and then they kind of moved on to Presto or Trino. That's why I'm saying Presto/Trino might even be good options here. I'm less familiar with this world of data processing. It's for when you're doing more analytic stuff and you've got a lot of data and you've got rare analytical queries. But those might even be other good options. If I was actually going to write this myself, though, I'd still stick with Cassandra because I'm actually familiar with that. But these might be fun options to explore over there. Okay. So thanks for watching. Hope this was interesting. I'll see you guys next time.